Hello everyone, welcome to today's section. So it's going to be section 4.6, which is about moment of a couple. So from today's objective, the students will be able to define what's a couple, and you'll be able to determine the moment of a couple in scalar and then in a vector analysis. So applications of couple moment. So day-to-day life we use couple moment without knowing the other couple. So what is a couple? So first application is like a steering wheel. So you're going to rotate the steering wheel. Let's say you're on the road and you're going to take a right turn. So you're going to rotate it in clockwise to take it a right turn. So in this case, you're going to be, let's assume that you are holding your hands at this position in 3 o'clock and then 9 o'clock position. You're holding the wheel and then you're rotating it. So with your hand, you're applying equal and then opposite forces to create that moment to turn your wheel. So that is a couple. So you have a equal and opposite forces divided by a perpendicular distance. So that's a couple. The other application, so you're going to be turning this. Again, you hold the hand and then you're going to rotate it. So you give the force. So you're going to rotate this wheel in anti-clockwise direction. Again, you're applying equal and opposite forces for turning it with a perpendicular distance of t. Then again, it's another application of couple. So what is a couple? I hope you have a understanding of couple. So couple are two parallel forces. Two parallel force with same magnitude, but it's going to be opposite in direction. And you will have a perpendicular distance t. So the conditions, parallel forces, two parallel forces, same magnitude, but opposite direction, and then it has a perpendicular distance. So what's the net force in this couple? So net force, so let's get this resultant of these forces. So first we have let's take in upward direction. So we have a negative F, and then we have a downward force. So that's negative F. So that gives me 0. So the net force is going to be 0 for our couple. But is the net moment is 0? No. Imagine you're applying these two forces, you're going to turn the wheel, right? So you're applying some kind of a moment. So this moment is defined by the force times your perpendicular distance. So for a couple, the negative force is always 0, but the negative moment is not equal to 0. So let's look into the vector formulation. So we know for scalar is just the force times the perpendicular distance. What happened in the vector? Previously we looked how we can find the moment in a vector formulation. So that's going to be the position vector from one point to the force. So here let's look this couple as a force in a 3D space. So just forget about the A. So consider the pipe is going to rotate about B. So that's going to be rotating like that. So we forget about the force at A. So you get the moment about A. So we're going to get the position vector from A to B. So that's going to be my moment. So my moment is going to be the position vector from A to B times my force. So now we have the other force, right? So here we neglected that. So let's consider that force. For considering that, let's assume my pipe is going to rotate about B. So now I don't consider about my force. So I'm going to take the position vector moving from B to A. So that's my RBA. And I don't consider that force. And now I have a negative F force. So my moment is going to be my position vector times negative F. So previously we get the moment from moving from A to B, and then we have the F. And now we have B to A, and then we have a negative F. Is these two equal? Yes, they are equal. How? Because we know that our position vector AB, it's equals to negative position vector of BA. So that gives me negative here, which makes me to get positive, which equates to same magnitude, right? So that's why we say that we create a moment with the same magnitude in the direction. So what are the properties of a couple? So first, couple is a free vector. Why is a free vector? Let's say this wheel, I'm applying a force and rotating it, so it's going to move in the clockwise direction. Let's change the position without changing the distance and the magnitude. I'm changing the position, still the distance is same, that's the diameter of the wheel, still the force, still the magnitude is same. Now I'm changing the position, again the distance is same, so my moment is still going to be F times d. So that's why this moment of a couple is always a free vector, because the couple only depends on the distance between the forces. So it can be moved anywhere on the body, having the same external effect on the body. The next property is, so these moments of due to the couples, they can be added together by using any vector addition. So we looked before to get the resultant forces, getting the addition of the forces. And then we get the resultant of our moments by getting the addition of all the moments, that is n is equals to 1 to I, how many acting. Similarly, we can get the addition of moments of this couple resultant by getting the couple moments, adding them together, right? So let's look into the scalar approach. So you have two couples that act on the beam with the geometry shown. So they're asked to find out this magnitude of F. So how do we do that? So one hint they have given that the resultant couple is going to be 1 kilonewton meter in the clockwise direction. So we know the addition of these two couples is going to be the addition of these moments. So we know that the resultant, let's write the resultant, so that's 1.5 in the clockwise direction. So that's going to be equal to first couple, that's my 2 times 0.3. Let's see the direction, how it's going to move. So because of this couple, it's going to create an anti-clockwise direction, that's positive. Let's look at my F. So F times the perpendicular distance is 0.9. So let's see which direction it's creating. So this F is creating in clockwise direction. So that's going to be negative. So I need to find my F. So I take F times 0.9 equals, I take F that side and bring 1.5 this side. So it's 2 times 0.3 plus 1.5. So that's going to give my magnitude of F, which is equals to 2.3 kilonewton. So it was simple. We just get the addition of the forces knowing the resultant. That's the scalar approach. Let's look into the vector approach. So they're given that force is equals to 80 Newton. So you're going to find out the direction of the couple moment. So let's look into this example. First I can go from A to B and get my position vectors. So let's say I'm taking this point as A and that point as B, and I'm going to get the position vector going from A to B. So let's get my coordinates so that I can find my position vector easily from there. So what's the coordinate of A? So it's 0.2 in X because it's 0.2 and 0.3 in the Y. Let's look at the coordinate of B. So that's 300 here in the X, and then 300 plus 300 plus 200, that's 0.8 in the Y. So that's my coordinate. So how do I get position vector from A to B? So I subtract the coordinates from B to A. So that's 0.3 minus 0.2I plus 0.8 minus 0.3J plus 0K because no Z components. So that's my RAB. So the final answer is going to be 0.1I plus 0.5J meters. So that's my position vector. Now let's look into my force. They say the magnitude of force is going to be F. So I know what to do now. So F is 80 kilonewton. So that's only in the vertical direction. So that's the vertical component. So that's just Newton. So now I have the position vector and F. So how do I get moment? So that's the cross product of my position vector times my force. So then I write it in a vector form. So that's my position vector and then my force. So simplifying this determinant, I would be able to get my moment of this force, which is going to be equals to 40I minus 8G Newton meter. So we mentioned previously that going from here and getting the moment, considering that only this force acts, and going from there considering only this force act and getting the moment here will be equal to the moment of the couple, right? So we got from RAB. Now let's try to go from RBA. So same things, we are going to get the coordinates of A and B. Previously, we know that. So the position vector is going to be the coordinate of A minus B, that's 0.3i plus 0.3 minus 0.8 j's. So which is going to be 0.1i plus minus 0.5 j and 0k. And my force is still going to be same, that's 80k Newton. So my moment is going to be RBA times my F. So I'm still going to write the determiner matrix. So that's 0.1, negative 0.5 and 0. That's 0, 0, and then it's going to be negative 80. So when I get the determinant of that, I'm going to get the same magnitude of the moment of the couple. So that's why we say it doesn't matter where you get the position vector, from A to B or B to A, it's going to be still same. Okay, so let's look at this example. This is a different example. So we have forces that are applied perpendicular in the frame. So they're asked to find out the magnitude of the couple moment and express it in the Cartesian vector. They asked to take the force in 80 Newton. So we know how to get that. So it's simple. We can use scalar here. So the moment we can get it as force times the perpendicular distance is directly given. So force is 80 times my perpendicular distance is 1.5. So that's going to be my magnitude. But the question here is they asked to find out the magnitude of moment and expresses in the vector form. So how do I express that? So that's my moment. So that's where it's applying, right? So that's the frame. So my moment is acting in that frame. So I wanted to get the x component. They say that frame makes 30 degrees. So I know the magnitude of my moment, that's 75 Newton meter. So I can get the x component of that by getting the cos 30. So that way I can get that component, my x component. So if I get the cos 30 as the x component, I can get the sin 30 to get my k component. So let's look at the direction, which is important. So this is going to be clockwise. So that's negative, negative, negative. So that gives me the final answer. So that's how I get the components in x and z directions. Let's look into the another problem. So we have two couples that act on a beam with a geometry shown and the distance is given with 4 feet. So first they asked to find a resultant couple of that two forces. So how do we do this one? So we can simply do vector. So one way we can resolve these forces in x and y direction and see whether we have a couple, and then we can solve from there. So let's take your time to solve this one, and if you cannot, come back to the video and see whether you can try that. So let's take the xy components of the 50 pounds that is acting. So my vertical component is 50 cos 30, and then my horizontal component 50 sin 30, and then 50 cos 30, and then again 50 sin 30. Let's see whether the components of this force produces a couple. Let's look at the horizontal forces. Will these form a couple? No, because they are collinear, right? And equal and opposite, and they are collinear. Our forces should be non-collinear, so that doesn't make a component. Only the vertical component with a perpendicular distance of 3 is going to make a couple. Now let's look at the 80 pounds. So we have 80 times 4 by 5 component, and then 80 times 3 by 5, and then we have 80 times 4 by 5, and then we have vertical components of 80 times 3 by 5. Will these vertical components make a couple again? No, because why? Again, they are going to be collinear. So if you look, they are going to be acting in the same line. So they don't make, so only the horizontal component with the 8. So we get the couple from there and we can get the resultant couple. Okay, so you can take your time and solve this problem. So they are given the magnitude of the forces, that is 80K. So you're asked to find out the couple. So that's what we did previously. So you can try it in your own and see whether you can solve the problem.